In example 3, we're verifying algebraically whether functions are even or odd using their algebraic definitions. Okay, so to be an even function, this definition, f of negative x equals f of x, that tells me to substitute in a negative x into the function everywhere I see x, simplify, and then if it's even, I get back the original function. Okay, this odd definition, f of negative x equals negative f of x, that tells me to substitute in a negative x everywhere I see x in the original function, simplify, and then I get back the opposite of f of x, or the negative of the function that I started with. Okay, so verifying algebraically means that we are going to write a proof. If you remember two-column proofs from geometry, that's what we're going to go ahead and do in this example. So we're going to start just like we did in geometry proofs with our first statement being the given information. And we were given the function f of x equals 4x squared minus 10. Okay, so that's how we'll always start these problems. Then the way we want to use this proof to verify algebraically is by showing that either the even definition or the odd definition up here in the corner is true. And in both of those, you can see they start with f of negative x. So our second step after we give the function that we're starting with, our second step is to substitute a negative x everywhere that we see x in the function. So f of negative x is equal to 4 and then times, and in the parentheses there, that's where my x would go, because see how it's 4x squared in my original minus 10, but in this spot where the x was in my original, right here, I'm going to replace that with a negative x instead. And so I'm looking for 4 times the quantity negative x squared minus 10. Okay, now my third step is to simplify this and see what I end up with. So when I had substituted f of negative x in for x in my function, now I'm going to take what is on this side and simplify. When I take a negative times a negative, because that's what negative x quantity squared means, it becomes positive. So I'll have 4x squared minus 10. And then I can see that what I ended with matches what I started with. When I put in a negative x for x, I get back 4x squared minus 10 from my original function. And that is the definition of an even function. So f of negative x, right, I have now shown is equal to what I started with, f of x. And then that's been verified. So you're going to go ahead and try example 3b on your own. So pause the video and list out your statements and reasons are given here, and then when you're ready to check, you can. Okay, so hopefully you've taken a second to fill this out on your own and give it a try, and we'll go ahead and work on it together now. So I'm starting with my given function, which was f of x equals negative 9 cube root of x. Okay, and then in my second step, because I'm going to use one of the definitions, I'm going to substitute negative x in for my x in the function. So f of negative x then will be equal to negative 9 cube root. And then my x that goes inside of that cube root, now I'm going to replace with negative x. And that is step number 2 in my two-column proof. Okay, then my simplify line, right, my goal is to make it match one of these definitions if possible. So either what I started with or the opposite of what I started with. Here, when I look at the cube root of a negative number, I know that cube root functions are odd functions, so they have symmetry about the line y equals x. So, for example, if I get my calculator here, I can show you what that looks like. So up here in the, oh, gotta turn it back on. So in the y equals, I'm gonna clear that out, and I'm gonna type in cube root, so let's do math down to cube root number 4. So there's my cube root of x, and instead of cube root of x, I'm going to put in cube root of negative x, because that's my line 2. Okay, and I'm going to go ahead and look at that graph, so zoom 6, and here's my sideways wiggle, right, for the cube root function. Okay, now if in my y equals, I'm going to show that because it's an odd function, right, it has that symmetry, rotational symmetry about the origin, that means that a reflection in the x-axis should produce the same graph as a reflection in the y-axis. So let's go ahead and test that out together here in the calculator and show that that's the case. So now instead of putting my negative inside here as the b, I'm going to put it out front as the a, right? So the first one, y1, that's a reflection in the y-axis. Now in y2, I would have a reflection in the x-axis. So I'm going to, just to show which one is which, I'm going to make the second one here a darker line. So you can see as we hit graph, there goes my darker line right over the top of the thinner one. And when you look at the table of ordered pairs, right, see how y1 and y2 match? So that's because these are the same function. So because they're odd, I can pull that negative out to the front then, and I'll have, when I simplify, f of negative x is equal to negative 9 times negative cube root of x, right? That's what we just showed in the graphing calculator was true. And now I have a negative times a negative, which will simplify to a positive. So f of negative x is now equal to positive 9 cube root of x. So now we want to see, have I matched that definition? So I've got f of negative x equals 9 cube root of x. When I compare that with what I started with, right, what I started with was negative 9 cube root of x. So do you see how I ended up with the opposite of what I started with? The only difference between these two is that negative right there. Right, now it's gone. So the definition for an odd function says when I put in a negative x, I get back the opposite, right, of what I started with. It doesn't mean that I have to end up here with a negative out front, right? What it means is that I end up with the opposite of f of x, which is what happened here. And so now I know that that is the definition of an odd function, and that f of negative x was equal to negative or opposite of f of x. So now you're going to go ahead and try example 3C on your own. So pause the video, and when you're ready to come back and check, we'll go over this together. Okay, so welcome back, and starting with our given information in line 1 of our proof, f of x is equal to the absolute value of the quantity x minus 5. Okay, then in step number 2, we're going to substitute a negative x in for all the x's we see. So the absolute value of negative x minus 5. Okay, and now in step 3, we want to simplify with the goal of making it match either the even or the odd definition. So when I substituted in that negative x, okay, now I want to see, can I make this match what I started with? So the only thing I can really see here that I could do, since these are both negative terms in the binomial, I could factor that negative to the front as a GCF. So let's try that. If I factor out that negative, now I'll have the quantity x plus 5 in my absolute value, because if I distributed, see how I would get back. So negative x, and then a negative times a positive is a negative 5. Okay, so now remember, absolute values make everything positive. So if I have a negative number inside my absolute value, that would simplify to f of negative x is equal to the absolute value of just that quantity x plus 5, because the absolute value is going to take that negative away anyway. Okay, and that's really as simplified as I'm going to get there. So when I compare my f of negative x to the original function I started with, I've got the absolute value of x minus 5 inside there, or the absolute value of the quantity x plus 5. And those are not opposites, right? The definition for odd is negative f of x. Right? If there was a way that I could have pulled that negative out front and kept the minus 5 inside, that would have been odd, but that's not what happened here. It's also not even, right? Because even functions, I put in a negative x, I get back what I started with exactly, and that didn't happen either. So this would be the definition of neither even nor odd. Okay, and that's because we showed that two things happened. We showed that f of negative x is not equal to, so slash through that equals, it is not equal to f of x, which says, hey, this is not even. But we also showed that f of negative x is not equal to negative f of x, right? And those two things together make up the definition of neither. So we know that this absolute value graph, which has been shifted 5 units to the right with our transformations, right? We see that that V-shaped graph shifted 5 units to the right is not centered at the y-axis, so it can't have y-axis symmetry. It's a V-shape, so it doesn't have rotational symmetry, and it's not at the origin, so it's definitely not odd either. And algebraically, right, then we can see that it's neither even nor odd.